This is a course on electricity and magnetism, therefore we have to cover Maxwell's equations. Maybe you've heard of Maxwell's equations. There's 4 of them, and we are in the 7th week of the class, and we've only done 1. We've only done Gauss's law. So we need to get going and move on to the next Maxwell's equation. So the next one we're going to do is Ampere's law. So when we did Gauss's law, we spent 5 boards talking about a new vector calculus concept called electric flux, thinking about the vector flux going through a surface. And then we got to Gauss's law. We're not going to do that this time. Ampere's law only requires a line integral going around a circle. And I think you're a little familiar with that. We've talked a lot about vectors and calculus now. I think you'll be okay. So we're going to go straight into Ampere's law. So here it is. The magnetic field along a closed surface, a closed path, sorry. The magnetic field along a closed path equals mu naught. Remember, that's the permeability of free space times the total current through the area enclosed by the path. That is my way of stating Ampere's law. It might be slightly different in your book. So let's put it in mathematical form. So the magnetic field along a closed path, really there what we mean is a line integral with a dot product. So the integral around a closed path of the magnetic field along, and when I said along, I really just meant B dotted with ds, the dot product of the B field along the step as you go around the path, equals mu naught I. Right? Mu naught times the current, where here we mean the current that's going through the path. So let's think about this a little bit, what this means. Let's think about it with a slightly complicated case of 2 wires carrying current. Here's one, and here's another one. Okay, and they both have current going out. Both have current going out like that, real close together. So we know, let's see, if we do a right-hand rule, that if we put our thumb along the current, the B fields are going to go around them. Now the B field in this case would do something kind of interesting. It would sort of make an oval around them. It would kind of dip there and come back here and go like that. So it's going to come, the B field is going to go around it like this and go around, and it's going to kind of dip and not have a value there because in between them, one's making a B field up and one's making a B field down. They're kind of canceling in between. So the field, you can imagine, would kind of do something like that and come down, do the opposite on the back side, and come back around. And it would do that all the way down the wire and get weaker as you go out. And all that stuff we already calculated with Biot-Savart. Okay? That's the B field. I haven't drawn anything else yet. Right? So now, let's think about 3 paths to consider. Okay? 3 Ampere's law kind of paths. So one might just say, let's just have a path going around both wires. Right? That's number 1, path around the wires. Well, let's apply Ampere's law and say, what would the integral of B dot ds, I'll call it ds1 just to be clear, around path 1b, it would be 2I. Okay? And also to be clear, I'll call these I naught. These are the current in each wire. That's equal to 2I naught. Okay? So you understand here I'm writing the general law. This is total. I total. Here I'm writing it for this specific case. So if we were to add up the B field here on this step, and 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 this step, all the way around, the magnitude of that thing would be 2I naught. And you can tell it's not 0, because everywhere you go around this path, B will go along the path. Right? B is not going in opposite directions along the path. You could also draw a smaller one here and just go around one of the wires. No problem, you can do that. And if you were to do that, as you come right around here, around ds, you'd get a lot of B field. And when you're around the middle, you wouldn't get much, because the B field kind of goes to 0 in between. Oh, and then you get more B field when you come out here. So when you do that integral around path 2, ds2 equals I naught. It would just be one of them. Okay? You'd just get one of the I naughts. And then, what else could you do? You could pick a path out here, just in space. Path 3. Well, number 3. The integral around b dot ds3 would equal 0, because there's no current going through it. Right? Number 1 had 2 I naughts going through it. Number 2 had 1. This one has none. So if you think about it, the B fields are going to kind of be up like this and kind of be up like that, going around the wires. So as you integrate along ds, you're going to get some positive b dot ds here and some negative b dot ds there. And they're going to cancel and give you 0. But we know it's going to be exactly 0 because there's no current going through those. Okay. So that's an example, a little bit of an example of how you use Ampere's law, or how it works, how it functions. It's always true. It's like Gauss's law. It's always true. It's only useful in cases of high symmetry, if you don't want to do a year of vector calculus. Okay? So now we're going to move on and see how can we use Ampere's law with symmetry to solve for B fields. Let's practice using Ampere's law in a case with symmetry to calculate the B, the magnetic field of a long, straight wire. We did it with the Biot-Savart law. Let's go ahead and also do it with Ampere's law. Make sure we get the same thing. So here is the wire in cross section. It has a radius A and current I. So now I'm going to draw it going away from you with some perspective to make it all, whoops, make it pretty like that, kind of going like that. Okay? So the current I flowing down the wire. We want to actually calculate it, the B field inside and outside. So let's think of this now. Let's imagine our coordinate system is here, our origin is here, and we want to go out in radius, and we want to draw our Amperian loops, is what they're called, in some real symmetric way. So we want to center them on the same axis as the wire, like that. So that would be one Amperian loop we want to consider, because it's symmetric. And keep in mind, in Ampere's law, they are loops. This is not a surface. This isn't a 2D representation of some surface cylinder. It's just a loop. I could draw it anywhere in the wire. I'm drawing it here because you can see it there. Okay? So that would be one. That would be the loop where r, the radius of that loop, is less than the radius of the wire. All right? That's actually inside the wire. Can we calculate the B field inside the wire? Yes, we can. We're going to. Okay, another one we might draw would be outside the wire, something like that. It would have a larger radius. It would be the radius greater than A. So this is outside. Both of these Amperian loops, you can see, are penetrated by some current. So it makes sense. We have a loop, current going through, we have a B field. It makes sense to use Ampere's law. It's actually easier to do the outside first. Okay? So let's do this loop. Okay. The integral of b dot ds as we go around. So now let's pick a point right here, say, and draw our ds. And what we know, due to symmetry, is that ds is going to be parallel to the B field right there. Okay? Because we know the B field basically goes around the wire. Okay? Now if you think back to doing the electric field of a point charge with Gauss's law, we sort of reconfirmed Coulomb's law. And I argued that I actually didn't use Coulomb's law at all. I just used symmetry to say certain things like this. Here, I'm kind of using our result from Biot-Savart to say that the B field goes around. You could get into deep symmetry arguments about the fact that the current goes this way, breaks the symmetry, therefore B has to be up or down. I don't want to all that confusing stuff. But it is true, though. We know it's okay for the B field to have a value this way because the current direction has broken the symmetry. It's not a charged rod. It's something carrying current in a specific way. Therefore, this way and that way are now different. But anyway, the symmetry of the situation I'm really referring to is the fact that we have a circular Amperian loop around a circular wire and they share the same axis. So the ds will always be parallel to the B field. Okay? If that's true, then they're parallel. It's just this magnitude times that magnitude. We can write it as the integral around the circle of B ds, where those are just magnitudes, I'm just writing them without the vector sign, is mu naught, and I, the total current I, goes through the loop. Okay. Symmetry also tells us something else, and that is that the magnitude of B is constant. Okay. When we go all the way around the Amperian loop, we're always at the same distance from the wire. There's nothing special about any one of these points relative to any of the other points. So there's no reason that the B should change. It should always be the same. So therefore, the B can come out of the integral. If the B comes out of the integral, we're left with the integral around a loop of ds. Well, like we just talked about, that's the circumference of the loop. So that's 2 pi times r, not a. It's the circumference of the loop. The loop's radius is r, the wire's radius is a. So B times 2 pi r equals mu naught I. Right? So then you're pretty much done. The B field around the wire, its magnitude is mu naught I over 2 pi r, which is the same thing we got when we applied the Biot-Savart law. And the direction is that it goes around, following the right-hand rule. If you put your thumb along the current in the wire, your fingers go around the direction of the B field. So that worked for outside the wire. Now let's do inside the wire. Okay, so this little loop inside the wire, I could draw a practice ds on it, like that. And we could say, due to symmetry, again, it's also true here, ds is parallel to B. And if there's current going through here, it's going to make a B field going around. It doesn't care if it's inside a metal. It won't shield the B field. Current outside won't make a difference. That's all basically the same. And it's also actually true that B will be constant going around this symmetric circle. There's no reason the B field would change going around that circle. So similar arguments. Then if it's B dot ds, then it turns into B times the integral of ds. Okay. The parallel part got rid of the dot product. The fact that B is constant brought it out of the integral. So this is looking pretty similar. E equals mu naught, but now is the difference, is the current. The current I, whenever you see current in a wire, you assume it's evenly distributed over the cross-section of the wire. It may not really be, but you assume it is, and usually you'll be told that the current is uniformly distributed through the wire. If that's the case, you have to figure out how much of that current is going through this circle. What fraction? Well, it's just by the area. Right? If the current is uniformly distributed across the cross-section of the wire, then you just need the fraction of the area that is inside that Amperian loop. So it's just pi r squared over pi a squared. That's the fraction times the total current, I. This is the fraction in the loop. Okay. And then, let's see, so then what do you got here? Then this becomes B times the integral around ds, that's 2 pi r, equals here, and then that cancels and that cancels. It's mu naught I r squared over a squared. And this is getting a little ugly, sorry. Let's see, if we bring the 2 pi r over here, I think you'll be able to see that in the end, it's mu naught I. And then we have a pi down in the bottom now. We have an r there, because that's r squared gets canceled by that r. And now in the bottom, we have pi a squared. Mu naught IR over, so we have 2 pi a squared, sorry, the 2 pi a squared. So that's the B field inside. Okay. You can kind of plot them. It's common to then look at it and say, oh, how do they go together? Well, the way they go together is if you were to plot the B field versus radius, and the wire looked like this, right? So there's the radius of the wire. It would increase linear with radius until you got up to here, right? So it increases linear with radius. And then it would fall as 1 over r when you get out here. So you'll see a plot like this a lot of times. That's how the magnitude of the B field increases with the radius as you're inside and outside the wire. Another check you can make is your two expressions had better be equal there. The B field can't go through some discontinuity. So at R equals A, sure enough, that becomes R equals A is mu naught I over 2 pi A, and that's mu naught I over 2 pi A. So everything makes sense. That was our first application of Ampere's law to solve for a B field. Let's see if Ampere's law fits in with the loopiness of the magnetic field. So integral of B dot ds around an Amperian loop equals mu naught times the current enclosed in that loop. And now let's draw a current loop to make the magnetic field. So we've thought about current loops a little bit. So there is a current loop. That's a loop of wire sitting not quite in the plane of board, kind of tilted towards you. I don't really want to draw the current direction because I'm going to draw a lot of fields all around it. In fact, I'm going to get this out of our way. So for now, let's just think about this. So we calculated the B field here earlier, and we calculated how the B field goes down as you get farther away. But early in learning sequence 6, we talked about how really this is what makes magnetic fields, and it tends to make them stick up like that in the middle, but then they tend to go around like this. Right? And then it goes around like that. And we might have one up here like that. This is really the north and the south pole of a magnetic field. If you have a current loop, in this case, right-hand rule says it would be going around from the back to the front like that. B would go up, north pole, south pole. And this is really the fundamental unit of the source of magnetism is a current loop. Let's stick a bunch of Amperian loops on it and see if Ampere's law makes sense. Write it again. So let's stick it one place here. So now I'm going to have it go around and enclose a little bit of the wire loop. Okay, we have many loops here. So this is the current carrying wire loop. This is now my Amperian loop that is interconnected. All right, and let's just think about it. That's all we're doing here is we're just thinking about fields. The B field is kind of going around with that Amperian loop. So if we walk around it this way with our DS's, like that, you can see that DS and B are always going to be more or less in the same direction. Therefore, you're going to get a big whopping value here, right? Adding up a bunch of positive things all the way around the loop, get a big number. So for that one, does the current penetrate the Amperian loop here? And the answer is yes. It had to have come through the Amperian loop right there. So that one works. Let's draw an Amperian loop sitting up here, kind of like a halo on the wire loop, the halo being yet another loop. So there's the Amperian loop sitting above the wire current loop. What would its situation be? Well, let's look at the other side first. Now for this Amperian loop, the right-hand side is going to be 0 because no current goes through that Amperian loop, right? All the current's down here. The loop's got nothing going through it. So do we get 0? Well, let's think about this. Here, the DS is going into the board. Here, it's going along the back. Here, it's coming out of you. And then here, it's going that way. So you can imagine the DS doing that. What is the B field doing? The B field, in this case, it's always kind of like that, right? It's coming out like that. And here it's coming out of the board. And here it's going into the board. So in actually every case, the B field is perpendicular to DS. You really have to visualize it in 3 dimensions, but everywhere you go, DS is around the circle. Everywhere you go, B is shooting away from the circle. So it's at weird angles with respect to the plane of the board, but it's always at 90 degrees to the path. Okay, like that. So in that case, this side is also 0, which is good. B is perpendicular to DS. No current goes through the loop. Let's draw another loop. This one, let's draw it in the plane of the board. Here, like that. Now, the current loop is sort of sitting like this, but this one is flat right here. If we go around it, we can have a ds this way on that side, a ds this way. Here we could have a ds that way. Here we could have a ds that way as we go around. Let's think about this side. What would b dot ds be? Well, here the b is kind of going up. So b is along ds. So we get a bunch of positive contributions to b dot ds. And then it goes sideways. They're perpendicular again at 0. But here, b is kind of against ds. Right? They're against each other. The dot product is negative. So you have some positive dot product on this side, some negative dot product on this side. They add up to 0. Right? So on this one, you'd get 0 here because it's nice and symmetric. Even if it were symmetric, the positives on one side, the negatives on the other side would cancel. And on the right-hand side, sure enough, there's no current going through that loop. Right? All the current's up here. The Amperian loop has no current going through it. So this was just some thinking and visualization to show you Ampere's law is always true. You'll always find anywhere you draw this loop. We could draw some crazy Amperian loop like this. And if you sit there and think about the direction of everything and the current, it'll always work. So we are now up to 2 of the Maxwell's equations. We have Ampere's law done, and we have Gauss's law. And we will very quickly knock out a third one. The third one is Gauss's law for magnetism. This is perhaps the most interesting one. And to understand it, I have to tell you the story of Blas Cabrera. So in the early 80s, Blas Cabrera was a professor, Stanford University, experimental physicist. And around that time, the superconducting materials were coming out. You could get superconducting wire, you could cool it down, and basically you could make a ring of the superconducting wire that was extremely sensitive to detect any chargy electromagnetic thing that might go through it. So he wanted to detect magnetic monopoles. So the question is, if there's charge for the electric field, why is there not charge for the magnetic field? A lot of theories would predict there's no reason there shouldn't be. But it seems like with the magnetic field, with everything that we observe, we're limited to just little loops. We think a current loop makes a magnetic field. It always has a north pole. It always has a south pole. Even though it's hard to envision, fundamentally there should just be just a north pole, a monopole, one pole, the equivalent of a charge. So the idea was maybe they're just hard to detect. Maybe there aren't many of them. So with these new superconducting materials, they could make detectors that might see them. So Cabrera was very ambitious. He said, I'm going to do this. He sets it up, cools it down, sets up all the electronics, very sophisticated experiment, and turns it on and just lets it go. And then on February 14th, 1981, he gets a perfect signature of a magnetic monopole going through the device. Exactly what the signature, the data should look like. It was officially the happiest a physicist has ever been on Valentine's Day. History of science, okay? So he's very excited. The whole lab is excited, and they watch to get another one, because then they could have an idea of how many monopoles are there. You see one a day, one a week, what do you see? So they watched, and they watched, and they watched, and they watched, and they never saw another magnetic monopole. They wrote it up. It's in physical review letters, and it's very clear in the abstract. We have seen one in 150 days. We saw one. Hundreds of other physicists set up their own magnetic monopole detectors because 3 people can get the Nobel Prize, right? So Cabrera, and now who finds the next 2? And no one to this day has ever found a magnetic monopole. So there may not be any. I like to think there's one, and it happened to fly through Stanford February 14th, 1981. I don't know. But the way we can tie that to a Maxwell's equation is Gauss's law for the electric field was just Gauss's law. And what did it tell you? It told you that if you have a charge, a magnetic or an electric charge inside a surface, a closed surface, that you would always get some flux, right? Because that charge is making an E field. So you would get a net E field coming out. Gauss's law for magnetism basically says that if you take any closed surface, we're doing a surface now, not Ampere's law, of B dot dA, you will never get a flux. It will never happen. If the universe were symmetric, you would say it's the magnetic charge over something, probably the permeability of free space or something. But the fact is, there are no magnetic charges. There are no magnetic monopoles. It's equal to 0. And this actually fits what we understand about the magnetic field. The way we draw it is that it's this field lines kind of going like this, and the field lines are always loopy, right? they always start and end on themselves. You never see a magnetic field line just coming off of an object. It's always looping around some other current loop. Therefore, any closed surface that you draw always has field lines going in, and it always has field lines going out. And there's no way to ever get a net magnetic field flux through a closed surface. The reason is because this side is 0. So sometimes it's usually referred to as Gauss's law for magnetism. It's really just the unnamed Maxwell's equation. Gauss's law for magnetism is a good name. I say forget it. Let's call it Cabrera's law, because he saw one. Maybe there's one. It's actually interesting. There are many physicists who search for things that don't exist. It's a weird phenomenon. Magnetic monopoles probably don't exist. Why would you look for it? One reason, maybe you'll find it. Maybe you'll be the one person to find it and you'll be famous. But it actually serves an important purpose, is because when he searched for 150 days and saw one, if they exist, he put an upper limit on how many there are in the universe. And then, when many other people searched for many years with bigger and bigger loops, they never saw one either. And they were lowering the upper limit of magnetic monopole density in the universe. And then other physicists, theorists, are writing cosmological theories about inflation and the Big Bang and all that stuff and how the universe works. Those will predict that, oh, there might be monopoles. And they'll predict a certain density. And if they predict a density that's higher than what we measured, that there aren't any, then that theory is wrong. And they have to go work on it. And they have to work on that theory some more and improve it to get their magnetic monopole density down to below the observed upper limit. So looking for things that don't exist actually serves an important purpose in science, even if you never find it.